Hello everyone. Today we are starting a new unit, a unit where we are going to examine things that repeat their motion over and over, like these vibrating masses on the end of springs. This is called oscillations, or if you will, oscillatory motion. These are motions that repeat themselves. These might be masses on springs or pendulums, or even the orbit of a planet around the sun. Right? Anything that repeats its motion over and over. And we're going to look at some specific kind of oscillators within this unit. But as we do that, there's a couple of ways that we describe oscillators, and that has to do kind of with the timing of them. Okay, one that we tend to use for things which take a good amount of time to complete a motion is we talk about that as being the period. Right? We've used this term period before. We talked about it as the time to go around once. Right? Well, in this case, period, which is a capital T, is the time for one complete oscillation. Right? One complete oscillation. So it has time units, seconds, minutes, hours, days, years, right? Something like that. Again, denoted by a capital T. Now, it's generally used for things that take a good amount of time, all right, to oscillate once. What about things that vibrate quickly, like a guitar string or a tuning fork or something like that? Right? Things that vibrate quickly, instead of defining them by their period, which we could, it would just be a really small number, right? We define them by how frequently they complete an oscillation. So frequency, lowercase f, okay, lowercase f for frequency, is the number of oscillations each unit of time. How many oscillations, how many vibrations do they complete each unit of time? For a mass on the end of a spring, if we start at the top, it would be how many times does it go from the top to the bottom, back to the top again, every second, every minute, every hour. Most commonly, we use units of oscillations per second, which are known as Hertz, named after a German by the name of Heinrich Hertz, who did a lot of work, sound and those kinds of things. Right? So sound vibrates very often in the order of hundreds of hertz, hundreds of oscillations every second. So 1 hertz is 1 oscillation per second. All right? A per second is a hertz. It's named after a guy, so it's a capital H, lowercase z. Now, if you think about these two quantities, period, the time for one complete oscillation, and frequency, the number of oscillations completed each unit of time, they are related to one another. Consider this. Let's say something has a period of, well, let's say this is around 2 seconds, right? To start at the top, go down to the bottom, go back up to the top, or to go from the right to the left, back to the right. If that's 2-second period, then how many oscillations does it complete each time, each second? Well, if it takes 2 seconds to do a whole one, in 1 second it'll only do a half, right? So the frequency would be 0.5 hertz. Well, what if the period was 5 seconds? Then how many oscillations would it complete each time? Well, now it would only complete 1/5 of an oscillation in a second. Do you see how those are related? Yeah, they're simply inverses of one another. Okay, so we can very quickly switch from a period to a frequency. And notice the units, right? If your period is in seconds, frequency is the inverse, 1/seconds, right? Or hertz, if we will. So they are related to one another by being inverses of one another. And again, it's traditional to use period when we're talking about things that take a decent amount of time, and frequency when we're talking about things that oscillate a lot, right? Very quickly. But that doesn't mean that we won't use, one of them otherwise. Right? Something with a very small frequency, right, just means it's not oscillating very fast. Something with a small period means that it very quickly does a full oscillation. Now, we're going to use masses on springs as kind of our paradigm object. We're going to spend several days here dealing with masses on springs and all the things that we can figure out about them. Okay? And then from there, we're going to build into things which are similar in some ways, as we will see. So let's consider this mass on a spring when the mass is just sitting there at rest. Okay, so unlike the previous page, it's not oscillating. It's not oscillating up and down or right and left. Okay? It's just sitting there. Well, what forces act on that mass? Of course, we have gravity acting down, and then we have the spring force acting up. And we know quite a bit about that spring force, right? As long as it's a cylindrical Hookean spring, we know some things about it that we'll talk about in a moment. But since the mass is just at rest, that means it's not accelerating. So how big are these forces? Well, they balance. Right? They have to balance since there's no acceleration. And that means the net force acting on this mass is 0. Now this ends up being a very important point in terms of defining an oscillation. Okay? And so this point where the net force is 0 is given a name. Right? It's called equilibrium. It's not the first time we've heard that term. Right? So the equilibrium position occurs when the net force is 0. With me there? Equilibrium occurs when the net force acting upon an object is 0. Now in class I would show you a little graph of that, but it's kind of hard to do in the computer, so let's just talk our way through it a little bit. Because notice something here about this net force. Okay? If the mass is below this equilibrium position, that would mean it stretches the spring more, that would mean the force exerted by the spring would be larger than gravity, which would tend to accelerate it back up towards equilibrium. If the mass was above the equilibrium position, shrinking the spring force, now gravity would be bigger than the spring force, and the net force would be down, pushing it back towards the equilibrium position. This is a process that is always going to be true for a certain kind of oscillatory object called simple harmonic motion, a simple harmonic oscillator. Okay, this is when a particle of mass m has a force that is proportional to the displacement of the particle, but opposite in sign. That displacement, by the way, being measured from the equilibrium position. So we tend to call the equilibrium position 0. Sometimes you'll see people doing it in other ways. I just like to call the equilibrium position 0 because, as you're going to see, it makes everything beautifully symmetric and makes life a little easier. Okay. So in this case, right, we're saying that the net force is proportional to the displacement, but opposite in direction. You might remember that back when we talked about springs, we called that a restoring force, a force that always acts towards the equilibrium position. Things that oscillate have to have that. Otherwise, like if the force was acting in the same direction as the displacement, that would mean it would be trying to push it further away from equilibrium and it would never come back. And of course, we know enough about springs to know that as long as it's a nice cylindrical Hookean spring, as I'm using in these GIFs, right, we know that the force exerted by the spring is negative kx. That's Hooke's law. Right? K is the spring constant, the strength of the spring in newtons per meter, and x is the elongation or compression. So notice here, Hooke's law is an example of a restoring force where the force exerted by the spring is proportional to its displacement, but opposite in direction. That would be important for, say, this one, right? The horizontal mass on a spring is kind of nice to analyze because then there's only one force. Now we're assuming no friction here, so perfect oscillation, okay? But then the only force making it oscillate is the force exerted by the spring. As we saw in the vertical case, things get a little more complex and we have to deal with net forces, right, in that case. Okay, so that's one of the reasons we tend to start with masses on springs, because we already know about the force exerted by a spring, as long as it's a Hookean spring, right? And we know that it fits this pattern, this first definition of several, all right, about what is simple harmonic motion. And by the way, you might see me abbreviate this as SHM sometimes, okay? All right, now, what exactly is simple harmonic motion? Well, let's take a step back. And let's think about something moving in uniform circular motion. Now, if you remember, UCM, or uniform circular motion as we defined it, is when something is moving in a circle at a constant speed. Right? Moving in a circle at a constant speed. Well, if we connect this with a reference line, right, from the axis of rotation to the object, we can think of this object as rotating, can't we? Right? This object is rotating about that point. And if it's rotating constantly, that we know because we just got out of the rotation unit, right? That we can describe that motion in rotational terms as having a constant angular velocity omega. And therefore, we can write an angular position function for this object as given by our constant angular velocity equation that we used in rotation, which is theta equals omega t plus theta naught. Final angular position equals the constant angular velocity times the time plus the initial angular position. If you notice, move this to the other side, that becomes angular displacement. And so really this is just angular displacement is angular velocity times time, right? That's constant angular velocity, okay? Now, here comes the fun part. Take that motion of that object moving in a circle and project it onto the horizontal plane. Now, what I mean by that is, what would it look like if you took a motion of something moving in a circle, but only looked at one dimension of it at a time, right? Put it on that horizontal plane as if you were shining a shadow down on it. Okay, watch this graphic. See that? You see how the black dot is the projection of the green dot onto the horizontal plane? I know, it's a tricky concept there. But I want you to notice something about that black dot. Isn't it moving in a motion that looks just like the motion we were just talking about of a mass on the end of a spring? Indeed it does, right? So in fact, we can link uniform circular motion and simple harmonic motion by saying that simple harmonic motion is the projection of uniform circular motion onto a diameter of the circle, onto an axis. Traditionally, we project this onto the horizontal axis, although we could do the vertical axis if we wished as well. But I'm going to stick to what AP does, which is to project it onto the horizontal axis. And that means that we can take some things we know about the uniform circular motion, green dot, and kind of map it onto the simple harmonic motion of the black dot. Okay, you ready for this? Oh, by the way, I pulled this off of the a pivot, which I thought was really good. So here you have an object moving in uniform circular motion, right? And do you see it matching up with the motion of the mass on a couple of springs? It's got a spring on either side and then a simple pendulum. See how that works, right? I love that. So I just borrowed that video because I thought it was pretty good. Right, so again, you got to kind of look at the circular motion on an edge, right? So if you look on it on edge, doesn't it look just like the motion of a mass on a spring or a pendulum? Right? They share very similar motions. So let's check it out when, let's say, the mass is here, okay? And then the projection of it would be here. Well, of course, we can draw in this, which would be the reference line, right, for where the object is in its circular motion, in its rotation, if you will. This would be at an angular position we could call theta. Of course, that distance is the radius of the circle it's moving in. Everybody okay with that? So those are all rotational things, right? This object, the green dot at this point, has an angular position theta, and it is a distance from the axis of rotation r, the radius of the circle. Well, note here, right, this would be the position of the black dot, of the projection, right, from the axis of rotation. Right? This would be how far away it is. Well, are these related? Indeed they are. Right? Drop a little vertical in there and look at the right triangle we have here, right? So couldn't we write this side as r cosine theta? You with me? So as theta changes, right, r cosine of theta would change, which changes the position, right, of this black dot. And so that means x, which is what we're going to call the position of the black dot because it's moving in the horizontal plane, right? Horizontal axis, if you will. So the position of the black dot is equal to r cosine theta at any point. And theta, if you remember, is a function of time given by omega t plus theta naught. So if we plug that in, we now get the position of the black dot as a function of time is given by r cosine of omega t plus theta naught. Okay, so it looks like here the position of this thing is going to be a cosine function. Huh. Okay. Well, and again, remember, this is if simple harmonic motion is the projection of uniform circular motion onto a diameter of the circle, right? Which it is. So, let's talk about this function, right, and the parts of this function. Okay, first of all, r is a constant, right? It's the radius of the circle here, okay? But notice here, as this thing goes around, right, x is going to vary, right? X could be anywhere from 0 when the particle is in the center to when it's here or here. How far away is it from the axis? Right? Well, at this point and this point, it is a distance r away. So r is also the maximum distance this point is from, or this point can reach from the equilibrium position. In terms of simple harmonic motion, we call that an oscillatory object's amplitude. Amplitude. I'm going to call this x sub m, which is what they use on AP sometimes. It stands for maximum displacement, right? Maximum displacement from the equilibrium position. So think of m as max here. Sometimes they use a capital A for amplitude, which certainly seems to fit a little better. But if you look on your equation sheet, you're going to see x sub m. So I'm going to use that. But just be aware that even on the AP test, even though they write the equation sheet as an x sub m, sometimes an A slips in there. It's a little weird that actually in AP1, they use a capital A for amplitude, right? But in APC, they use x sub m, maximum displacement. Now be careful. The amplitude of this oscillatory motion, this black dot, isn't from one edge all the way to the other. It's the displacement from equilibrium. So it's from here to the edge, right? And from here to the edge. I mean, think of the cosine function, right, as oscillating between -1 and 1. Right? So when it's -1, now the object's over here. When the cosine is 1, now the object's over there. And in between, it'll be somewhere in between. Now, theta sub naught is going to be the starting position, right, of the green dot, which is also the starting position, if you will, of the black dot. Okay? So rather than call it starting position, it's got a special name, everything does. It's called a phase angle, or sometimes known as a phase constant. It's defined by the Greek letter lowercase phi, okay, and a little circle with a slash through it, okay? It's a phi. So this is the starting point of the motion, okay? It depends on where does it start from at t equals 0. We tend to think of phi as being 0 when the black dot is at a positive amplitude. So when it starts here, we say that it's starting from 0. Now, this is completely analogous to the uniform circular motion, right? If we're talking about rotational motion, we call 0, in terms of like the angle, right, out at the positive horizontal. Right? And then we go from 0 around to 360, right, degrees here. So the phase angle is where does it start from, okay? I know, it's getting complex, all right? So again, like I said, important to realize when is phi 0? It's when it starts at the positive maximum. We're going to try to do that as often as possible. Okay? In AP1, they don't even worry about this part. They're just worrying about the oscillatory part, but we have to throw in the phase angle on occasion. Okay. So here's the function. Now, I want to show you a simulation here. If we were in class, you would have already seen this kind of oscillate, but let's see, I don't want to end show. I want to go here. So let me show you, okay, this. So here's a mass on the end of a spring, okay? I'm going to pick up the block. So it's in the equilibrium position right now. This is just where it sits. I'm going to raise it above the equilibrium position. This would be positive amplitude. right? Positive amplitude. This will be as high as it goes. Then I'm going to let it go. And when I do, it's going to create a position versus time graph. You ready? So there's the position versus time graph for this. At 0, it was at the positive horizontal. Right? Every time it passes through the equilibrium position, it passes through 0 here on the graph. Note the shape of this, right? And all of you should have had enough trig by now, right, to see that as a trig function. We're going to do a little bit of this with Logger Pro and some other things in here, but this is the position versus time graph, okay, for this kind of motion, for simple harmonic motion. So let's see, stopping that and going back. This gives us a second definition for simple harmonic motion. So here's the first one, right? The force is proportional to the displacement but opposite in direction. It's also, simple harmonic motion can be described with a periodic motion in which the position is a sinusoidal function of time. That's a really fun word. Try saying that. Sinusoidal function of time. That means when we graph position as a function of time, we get, a cosine sine curve. Now we're writing it as a cosine function, as we see up here, because of where we're defining 0 phase angle to be, which is at the highest point, right, or the positive amplitude. Hey, you could just as easily write this as a sine function. You'd just be starting at a different 0. Okay, but traditionally, okay, on the AP test, we write it as a cosine function, but it's still called sinusoidal because it has that function shape. Right, so when you do a position versus time graph of a motion and it looks sinusoidal, that means it's simple harmonic motion. Now we have one more thing to discuss, right? Because t is just time, right? So we know that this is the amplitude, this is the phase angle or the phase constant where it starts from. What's omega? Well, omega is angular velocity, right, in rotational motion, in the motion of the green dot going around in a circle. But in oscillatory motion, we are going to call this the angular frequency. And we use the exact same symbol. I know, a little weird, right? We use the exact same symbol, omega. So here's the definition of angular frequency. It's the rate of change of angular displacement of an oscillating object. Remember, frequency is how many oscillations every second. So this is kind of a similar idea, right? But it's how much does the angular displacement change every second. So that means angular frequency can be written as delta theta over delta t, right? Angular displacement over time. But you'll notice that's the exact same way we wrote angular velocity, right? At least for a constant angular velocity. So, we're going to write the angular frequency the same way, except we're interpreting it different. This is now going to talk about the oscillation that it's going through, the simple harmonic motion, the vibration, right, as opposed to a particle moving in a circle. For one complete oscillation, right, that would be one complete rotation of the object, right? What's the angular displacement for one complete rotation? Well, it is, of course, 2 pi radians. And the time for one complete oscillation, as we defined earlier, is the period. So one complete oscillation of something in simple harmonic motion, the mass on the end of a spring starting out on the right, going to the left, coming all the way back to the right again, one complete motion, is 2 pi radians. Yeah, radians are going to be huge in this unit, okay? We're even going to sometimes use time in terms of pi and things, okay? Because it's just kind of how we do things when we deal with this relationship between uniform circular motion and simple harmonic motion. So this is a nice thing to remember, how to convert. So you can find omega in terms of the period. Or remember, since period is inversely proportional to the frequency, right? We can also write the angular frequency as 2 pi times the linear frequency. Okay? F is linear frequency or frequency, right? T is period, omega is angular frequency. So we can convert between these, and it's really the conversion is the 2 pi, again, because we're combining uniform circular motion, right, where one complete motion you go through 2 pi radians, right, of angle, or angular displacement. And so in simple harmonic motion, one complete vibration, from where you start to the other end and back again, is 2 pi radians of oscillation as well. Ooh, see the relationship here. It's a tough one, but it works. Oh, the units, by the way, of angular frequency are, of course, the same units as angular velocity, radians per second. So this is how many radians it's oscillating through every second. 2 pi radians is in a complete oscillation, from the right to the left, back to the right again. Pi radians is half an oscillation, from the right to the left. Right? And we can break it up into fractional pies and all that stuff, and we are going to do that as we work through understanding the kinematics of simple harmonic motion.